Something I've been doing recently is forking open source libraries and modifying the code to return kind of intermediate steps so I can better understand what's happening under the hood. Also, it helps me validate my understanding of the concepts that are at play. So in this video, I'm going to show what I recently did with the peft library to understand how the merge and unload function works, method works. And this was part of a broader problem that I was trying to solve, where when I load a LoRA model from Hugging Face, where it has the adapters, and I pass some inputs through it and get some outputs, and then I merge the model with the base model, pass the inputs through it, and get outputs. The unmerged and merged LoRA model outputs are not equal. They're significantly different. And so I was trying to understand why this was the case. I had seen things on the forum from, the, admin and leaders that said that, some difference is expected when you merge models. And but I wanted to understand why exactly that was. And so one thing I thought of was like, okay, maybe there's something going on in merge and unload where, I don't know, some operation takes place where the model weights slightly change for some reason. Spoiler alert, that's not the case. And I'm going to do a future video where I do show my understanding of why the merged and unmerged model outputs are different. But as part of this process, I got to exercise my diagnosing, debugging muscles, and so I wanted to show what that looked like. So the first thing you want to do is obviously you want to fork the open source library. So peft is the library in question. And then I usually like to keep the main branch in sync with the original repo. And so anything I'm editing, I create a new branch. So I created a merge and unload debug branch. And Colab already has peft installed, so you have to uninstall that first. And then you can install your branch's version, like so. And so now I have my branch. I have control over, the code. I can make edits, make changes, return things whenever I want to inspect them. And so it's honestly, like, it's a really empowering experience. It's really fun, and it's a great way to learn about what's going on under the hood. So that's what I've done here. And then here are my imports for the different things I'm going to use. I'm using a small LM135 million base model, and then I have some LoRa adapters that are just as an experiment. So I'm loading that with peft model from pre-trained and just making sure that everything is on the GPU. So we're going to take a quick look at what this model is, and under the hood it's a LoRa model. And if we look at the function merge and unload, we can see that all it really does is it returns the output of unload and optionally merge. So I had put a print statement before this just to make sure that when I do call merge and unload, it actually does call this, and it does. And so then the next step I did was take a look at this line, which is optionally unload and optionally merge. And another great thing about open source is that you can just call these intermediate functions and methods, and you can understand, you can recreate the logic so you can understand what's going on. So get submodules is part of the peft utils other library, or I guess module, and then I think that's the only one that we need here. So basically what I'm going to do in my notebook is I'm going to check this code so I can understand it, so that I can dig in deeper. So first we have this keyless line where self is the adapters, the unmerged adapters. So I'm going to run that, and I'm choosing to focus on the qproj layer in the self-attention module in the first layer of the model. And so that way I'm gonna, fix it to something that I can easily access. So that's what keylist does. It gets a list of all of the modules that are named in your model. And then we try to get submodules given the model and given the key, and it returns a parent, target, and target name. So that's what I'll do here. So here's the parent. So here's qproj, and the parent is the llama attention module. The target is the qproj, which is a LoRa linear layer. So here's the base layer, here's the LoRa A adapter, and here's the LoRa B adapter. And then the target name is qproj. So far so good. Model.layers.0.selfattention.qproj is what I expect it to be. Okay, then we have a couple of checks. If it has, this attribute, then it's going to run this code. Otherwise, if it has the base layer attribute, then it's going to call target.merge. So I'm going to run those two. This is false, and this is true. So because it's true, it will run target.merge. I also saw that it had as a separate named module the base layer. So I wanted to understand, does that interact with this qproj in any way? And so I pull that out. So here's the parent. So the parent is now qproj because the child is base layer. Here's the base layer, and the target name is base layer. And then we run these two checks again to see if any of this code will run. And this one is false and this one is false. So okay, I know that the module names related to qproj are the only one of interest is qproj itself. qproj.baselayer does not interact with this in any way, at least for our purposes. Okay, so that gave me enough information to say, okay, this is going to be true. So now I added this line. So I said, okay, if merge is true, and if the target name is qproj, then run target merge. And then I modified target merge so that it would return these weights. And then I inserted this return line so that it would return when you call merge and unload. It would go through this first layer with the first qproj, and then it would return these weights. So I'm basically injecting some code to interrupt the full sequence of merge and unload so I can inspect what's happening for a very small, focus use case. All right, so where we're going to go next is target.merge. And if you look at the symbol definition results, there's tons of merges because there's tons of different tuners. So we're going to manually go to LoRa layer.py and have merge here. And if we scroll up, this is a linear layer. So I'm going to grab the get target merge. We can see here that it has all this code, and we're going to look at that in a little more detail. And then we can see it's also peft tuners LoRa layer.py. Okay, so we're doing good. So, all right, let's go back down to merge. So first thing, it's going to check adapters to merge. So this again comes from one of the utils. This one comes from peft.tuners.tunersutils. So I can import that. I get back a list of adapters and it's default. And we look at the LoRa keys and we see default in there as well. So adapter names is going to be a list, and it's going to loop through each of the adapter names in that list. And then active adapter is default. Okay, cool. So if active adapter in self.lora.keys, that's the next checks. So here's target LoRa.keys. And let me see something here. Yeah, okay, cool. So I'm going to iterate through self.lora.keys, and it's just going to be a single key of default. All right, so let's take a look at what happens next. So we have base layer, which is self.getBaseLayer. So this is our base layer, and I'm going to make a copy of this because I want to return the original base layer weights to inspect them. So I do deep copy base layer dot weight, and I store that in OG base layer weight. Safe merge is false, so I don't have to worry about that. So I can go down here to this else block, and it takes the active adapter, passes it to get delta weight, and it gives me the delta weight. So let's take a look at delta weight. And yeah, so that's where we are so far. So get delta weight is doing a number of things. It's going to, if you want to cast it to floating point 32, then it's going to do that. Otherwise, the main line is this one here. So it takes the LoRa B weight, matrix multiplies with LoRa A weight, and then multiplies it by the scaling factor. So this is the change in adapter weights, or sorry, change in base layer weights that we have learned during training. So I'm going to copy this for use later on, but I just wanted to poke in here and show what get delta weight looks like. All right, so that's that one here. I'm also printing the data type because I was curious of what that was. An initial kind of hypothesis I had was like, oh, maybe the data type changes somewhere in the code, and maybe that's why there's this difference in outputs between merged and unmerged models. That wasn't really the case, but so that was something I did. Are we using LoRA? No, we're not. So this if not self-use LoRA, so self-use LoRA is false. If not false is true. And so I'm going to print the base layer data type, and then this line is already what peft does, where it takes the delta weight and it adds it to the base layer weight. This is why I made a deep copy of the base layer weight, because it modifies this in place. LoRa bias is false, so this is not going to run, and it appends this to the list of merged adapters. So that's just that default string. And then this is what I added here, is I'm going to return the original base layer weight of the base model. I'm going to return the delta weight, which is LoRa B, LoRa A matrix multiplied times scaling factor. And then I'm going to return the final weight, which is the base layer weight plus the delta weight. So these are the things that I wanted to inspect. So I'm going to run this now. So this is now merge and unload. So this should run my print statements, and it should return the weights that I asked. Key thing to note is that the LoRa weights are in float 32, but the final base layer weight is in bfloat 16. So we'll make sure to do that when we recreate the calculations. And if we look at the data types, the original base layer is bfloat 16, so is the final, and then the delta weight is float 32. All right, so I'm going to now reload the base model and reload the adapters, because when you do adapters.merge and unload, it changes the base model. It merges the base model. So I got to get a fresh copy so I can actually look at the adapters. And what I'm going to do now is I'm going to see if I can recreate delta weight and the final weight with the concepts that I've understood about LoRa and that we saw in these files. So if we look at adapters, we go base model, model, layers, 0, self-attention, qproj. So that's how we're going to get to our target here, which is what's happening here. Cool. So we do that, and here's our qproj. Then I'm going to pluck out LoRa B and LoRa A, which you can see here. And then we'll look at the shapes. So 64 out, 576 in, 576 out, 64 in. So that's these shapes. And just confirming that, yes, they are indeed float 32. So even though the model is BF16, the LoRa weights are float 32. That was something I did not know before I did this. I'm going to get the scaling factor, which is 2.0. And then I'm going to look at the base layer, and I'm going to compare it with the OG base layer that we returned from merge and unload, and both are bfloat 16. So now I'm going to recreate delta weight, which is this output layer or output tensor that we saw here. While we're looking at this, let's look at qproj fan in, fan out. This is a really important attribute. and it's false, because if you look at these layers, this is basically saying, are the weights stored as in comma out? And they're not, right? So here's output features 64, input features 576. So this is out comma in, and this is out comma in. So this is false. And then if we look at, where'd it go? Transpose, which is in utils.other. We can see that if the weights are not stored as in comma out, we don't transpose. We just return the weights. So really important attribute here. Something you want to make sure is correct, because if it's true, then it'll return weight.transpose. So it's not true, it's not false, so it's going to return, let me see. Yeah. So it's going to return the weight. So, okay. So basically what this means is that this is not going to change the weights. It's not going to transpose it, because this is out comma in, which is the expected outcome. Okay, so I do LoRA B, matrix multiplied with LoRA A, and then I multiply by the scaling factor. And this is also why this is important to look at, because you can't tell from the output dimensions whether or not it needs to be transposed, because it's a square matrix. Okay, so now I can look at my manually selected base layer weight and the OG base layer weight, and they are equal. I can look at my manually calculated delta weight and the delta weight returned from within merge and unload. They are equal. And then I have my final weight, which is my base layer weight data plus the output tensor, and this is float 32. So I got to convert it to bfloat 16 to match the base layer final weight from merge and unload, and that's true. So in this way, I kind of systematically looked at and inspected each of the weight matrices, and I'm like, okay, I don't think the difference between the merged and unmerged models is because of how these weight matrices are handled. So this kind of eliminated one kind of major debugging source for my original question. And as a result, I have a better understanding of the peft library. I have a better understanding of LoRA. It was a great review to kind of go through some of these calculations to understand again and remind myself how LoRA works. So yeah, that is my video for this topic. I'm going to make at least, I think, 2 more videos around this issue of merged and unmerged LoRA models resulting in different outputs. So be on the lookout for those. Thanks for watching, and I'll see you next time.